Hello viewers, this is Wargadaruna taking you through the story of A-level applied mathematics. In this video I'm going to go through the topic of root location and approximation. So this topic is under numerical methods and is suitable for students in both senior 5 and senior 6, offering principal mathematics as part of their combination. So before we start our topic, I would like to remind ourselves of the progress on this platform. So on this platform so far, what is ticked is what has been covered in Math Paper 2. Like I told you, Math Paper 2 is divided into 3 parts. There is mechanics, statistics and probability, and lastly numerical methods. Now for mechanics is further subdivided into 3 parts. One is kinematics, and in it one question in section A, one question in section B, and these are the topics, and I think you realize that we have covered almost all of them. Now this one, which is half ticked, so half ticks mean that the video was uploaded at the very first time we opened the YouTube channel, and by that time the video quality was not that okay, so plans are being made to remake the videos. So the next part of mechanics is dynamics, and these are the topics. This is the coverage, and you expect one question in section A, one question in section B in a standard paper. And the last part of mechanics is statics. Now kinematics deals with motion without a force being applied, dynamics deals with motion when there's a force being applied, and statics deals with equilibrium, or forces in equilibrium. So these are the topics, and this is the coverage. Then when you go to probability and statistics, this is the coverage, and these are the topics, and the pending topic is permutation and combination. Then for numerical methods, we have so far covered these first 3, and in this video we are going to add on this one for root location and approximation, and we shall be left with only one topic, and that will be flow charts to complete this section of mechanics and be ready and be sure for 2 questions in section A and 2 questions in section B in your UNEB or in any standard paper like a mock paper. So with that introduction, we shall now go to our topic of root location and approximation. So let's start with root location. So when there is no direct method of solving an equation, an attempt may be made to first locate the roots. So here we deal with root location and root approximation, and I think you know that we are using the word approximation because all numerical methods deal with getting approximate values. So now suppose we wish to solve an equation fx equal to 0 and that fx is continuous in the interval from A to B. If it has been established that fa and fb are of opposite signs, know this word, opposite signs, i.e. their product, remember when you multiply a positive number with a negative number, you get a negative number, and that negative number must be less than 0. Therefore, when you multiply if these are of opposite signs, one will be positive, another one will be negative. Therefore, when you multiply them, the outcome will be less than 0. It implies that there is at least one, know this word at least, so there can be one or more, so there is at least one real root of the equation of fx equal to 0 between x equal to a and x equal to b. So let's see what we mean by this slide. So question 1 says locate. Note that we are dealing under, we are now under root location. So we have to locate each of the 3 roots of the equation this. So here what we do, we shall know that our fx is now this, because we say that the formula has to be fx equal to 0. So fx equal to 0, it implies that this 0 is catered for by this one will become our fx. So everything, all the terms are put on one side, and that means that it will be equated to 0. Therefore the ones on this side will become our fx. So next we shall tabulate our values. So tabulating, we shall tabulate values of -3. So how do you know which value to start with and which value to end? We shall come to that. So when I put -3 where there is x, I'll come up with -17. Then next is -2. When I put -2 where there is x, next the value will be -1. Then when I put -1, it will be 3. When I put 0, f0 will be 1. When I put 1, f1 will be -1. And when I put 2, f2 will be 3. When I put 3, f2 will be 19. So now after tabulating, next is to look for change of sign. So when you look at this value and this value is negative, this is positive, meaning that there's a change of sign from x equal to 1 to -2 and x equal to -1. Therefore, what does that mean? It implies that there is a root between x equal to -1 and x equal to -2. Another change of sign is from your tier, meaning there's a root between 0 and 1. Another change of sign is from your tier, meaning that there's a root between 1 and 2. So basically that's what they wanted you to do, because they wanted you to locate the roots. Now how do you know that my values should start from -3 up to +3? So here, like I told you, numerical methods we use approximate values, but you can still use a calculator to get the roots of this cubic equation. When you get after getting the roots of this cubic equation, you must list your values such that your interval encloses all those 3 roots. So B1 for this, B1 for generating that, B1 for the first location, B1 for the second location, B1 for the third location. So that was question 1. Now we shall go to question 2. Question 2 says, locate each of the 3 roots of the equation that. So the first thing to do is to rearrange. So when I rearrange, I'll bring all these ones on this side. For example, when I bring this one on this side, it will become x power 5 minus 3x squared plus 1. And that will be our fx, because when you bring it this side, it will be equated to 0. Next is to tabulate our values. So when I tabulate -3, when I put -3 here, f -3 will be -269. Then when I put -2, f -2 will be -43. When I put -1, f will be -3. When I put 0, f will be 1. When I put 1, f will be -1. And when I put 2, f will be 21. When I put 3, f will be 217. So when you get the 3 roots, we can stop. For example, if you look at this, there is a change of sign from your tier, meaning that there is a root between -1 and 0. Then there's a change of sign from your tier, meaning there is a root between 0 and 1. And there's a change of sign from your tier, meaning there's a root between 1 and 2. So basically that's what they wanted you to do. So B1, 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 B1. So that was question 2. Now we shall go to question 3, which says show that the equation, this one, has a root between this and this. Now previously in the first 2 questions you were locating a root, we are locating the roots, but now this time they have given you the range where the root lies. So how do you do such a question? What you do, you have to first rearrange to get your fx. So when I rearrange, I'll realize that this is my fx. Now after that, next is to use physical substitution. Now, what does physical substitution mean? It means that you get this -4 here and substitute it to wherever there is x. So this part is needed. This is what we call physical substitution, to show to show how you are substituting. Now next is because there is a trigonometric function, then the calculator has to be in radians. So each time there is a trig function like cos, sine, tan, sec, cosec, cot, the calculator has to be in radians. So when it is in radians, you'll come up with this value. So like we said in math 2, when they don't specify the number of decimal places, you have to use 4. So next is to bring this negative 3 and put it here, then you come up with negative 0.9900. So I think we realize that there is a change of sign, because this is negative, this is positive. Now that change of sign is enough proof to show that there is a root between negative 4 and negative 3. So we shall come and conclude that since f of negative 4 multiplied by f of negative 3 is less than 0, it implies that there is a root between negative 4 and negative 3. So basically that is what they wanted in this question. So M1 for this physical substitution, B1 for the output, physical substitution, output, conclusion. So that was question 3. Now we shall go to question 4, which says that show that the equation this has a real root between 1 and 1.5. So we shall still go through the same procedure, rearrange to get your fx. Therefore fx is this whole part, which is that. Next is to use physical substitutions. When I put 1 here, I'll come up with that value, and when I put 1.5 here, I'll come up with that value. So because there is a trig function here, the calculator has to be set in radians. That is how you'll be able to get these values. So next is to conclude that since there is a change of sign, or since their product is less than 0, it implies that there is a root between x equal to 1 and x equal to 1.5. So basically that's what they wanted. Now let's see how much can be awarded. So M1 for substitution, physical substitution, B1 for output, M1 for physical substitution, B1 for output, B1 for conclusion. So that was question 4. Now we shall go to question 5, which says that show that the root of the equation this lies between x equal to 1 and x equal to 1.5. So still we shall have to do the same procedure, rearrange so that you can easily get your fx, then do physical substitution for x equal to 1 and also for x equal to x equal to 1.5, then you conclude. So M1 for physical substitution, B1 for output, M1 for physical substitution, B1 for output, and B1 for conclusion. So that was root location. Remember the topic is divided into 2, root location and root approximation. So root approximation is what we are going to start on now. So under root approximation we have 2 terms. There is what we call initial approximation of the root and what we call a beta approximation of the root. We shall see what all these terms mean. So for root initial approximation, we shall come and say that after locating the interval within which the real root is of a given function lies, the initial approximation of this root can then be obtained using either linear interpolation method. I think we learned linear interpolation in the previous videos, or graphical method, depending on how the question is asked. So sometimes the question will say using linear interpolation find the initial approximation, or using graphical method find the initial approximation, or the question will be left open whereby they don't state which method to use. So we shall see all those 3 parts. One where they specify that using linear interpolation, another one where they specify that use graphical method, and another one where they don't specify. So when they don't specify, what do you do? So we shall see all that. Then another part of the approximate root is what we call a beta approximation of the root. So once the approximate value of the root of the function or a given equation has been established, there are more efficient methods of approximating closer to the roots. Like I told you, under numerical methods, all the methods are used to approximate. So this is achieved by performing an iteration or iterative process. So iteration, by definition, an iteration is a process of obtaining successive approximations by repeating the standard process. So we shall see what this means in the worked examples. So we perform an iteration either by Newton-Raphson method or by the general form iterative method or by linear interpolation. I think realize that linear interpolation can be used to get both roots, can be used to get the initial approximation of the root, and can also be used to get a beta approximation of the root. The Newton-Raphson method is used only to get a beta approximation of the root, and also general form iterative method can be used to only get a beta approximation of the root. So I believe that in this part, what you already know is linear interpolation, because you have ever heard of it, but Newton-Raphson method you have not yet heard of it, and also general iterative method you have also not yet heard of it, and also the word iteration. So that is what we are going to concentrate on. So we are going to start with Newton-Raphson method because this one is the core of this topic. Newton-Raphson method is the core, and because it is the core, its formula, you don't need to cram it. It is already available in your mathematical tables. So if you look at your mathematical tables at the back, under the section of numerical methods, or you look at number 60 of those list of formulae, you realize that there is a formula of Newton-Raphson and says if xn is an approximate root of fx equal to 0, then xn plus 1 is equal to xn minus fxn divided by f prime xn, where n is an integer, where n is a whole number, or which starts from 0, 1, 2, and so on, is generally a beta approximation. So a beta approximation is this one, which is xn plus 1. So under this extract of numerical methods, the main topic, we have already covered this one under the topic of trapezium rule, and I believe you know how to use it. And now in this topic, we are going to concentrate more or put more emphasis on Newton-Raphson method because it appears almost in all the parts of the remaining part of this topic. So Newton-Raphson method is one of the iterative methods. Remember we saw that the methods are 1 Newton-Raphson method, 2 general form iterative method, and 3 linear interpolation. So Newton-Raphson is one of the iterative method used in finding the solution of an equation in the form fx equal to 0. So if xn plus 1 is a beta approximation of the solution of fx equal to 0, it implies that xn plus 1 is equal to xn minus fxn divided by f prime xn. So this f prime xn is a derivative of this, and we shall see how it is got, where n starts from 0 and onwards. So I think you see that we didn't put the limit where n ends, so we shall see how to know where to stop as we are carrying out the iteration. So this is Newton-Raphson iterative formula and can be used on any type of equation provided it's a single variable. So Newton-Raphson method, that is why I told you that this is the core, because it is not restricted. Any formula, as long, even if it's a polynomial or transcendental, so transcendental means it can contain a trig function or an exponential or a natural logarithm. So all those form equations, this formula can be used to get their better approximation. But for general form iterative method, as we shall see, it is only restricted to polynomials. So given the initial approximation x naught, remember we have already seen the methods used to get the initial approximation, and in the worked examples we shall see how to get it. The process can be repeated. Note this word repeated, because we are dealing with iterations, so you have to repeat the process for a given number of iterations to obtain the successive approximations x1, x2, x3, and so on. I think you also realize that we have not put the end where to stop, so we shall see in the examples. So how do you know where to stop? For you to know where to stop, it depends on a term called tolerance. So using the recurrence formula, i.e. each approximation is derived from the previous one by the same formula until the difference in the two consecutive approximations is less than the tolerance. So this tol means tolerance, and the formula for tolerance is the same as the formula for error in a single term, so it will be equal to 0.5 times 10 to power negative n, where n is the number of decimal places. But because we have used already n here, we shall not use n, we can use k or any symbol to mean number of decimal places. So that was introducing you to Newton-Raphson. Now we are going to see how it is used. So we shall start with question 1, which came from UNEB 2016, paper 2, question 11, and says, given the equation this, part A, show that the equation has a root between -1 and 0. Then 2, part B, Roman 1. So I think let's start with part A, to show that the equation has a root between -1 and 0. I think that one you have already seen it in the previous part, so let's first do that quickly. So you come and say that our fx is equal to this given equation, therefore use physical substitution. When x is -1, you'll come up with -14, and when x is 0, you'll come up with 2. So I think you realize that there's a change of sign, therefore you'll come and conclude that since this product is less than 0, then there is a root between -1 and 0. So basically that's what they wanted in part A. So now we shall go to part B, Roman 1. Part B, Roman 1 says, show that the Newton-Raphson formula for approximating the root of the equation is given by this. So the Newton-Raphson formula for this equation is given by this. So let's do that. So first of all, you already know that for Newton-Raphson formula, you have to first get fx and f and its derivative. So this one is here, so next is to get its derivative. So when I differentiate x cubed, I'll come up with 3x squared. When I differentiate this, I'll come up with 12x. Differentiate this, I'll come up with 9. Differentiate this, I'll come up with 0. So next is to quote Newton-Raphson formula. So here we have to quote, and I think realize that when I was getting the derivative, I didn't put this n here. So always be keen, don't put it there at this point. You only put it in the formula because the formula has xn, and we shall see why that is there. So that is very, very vital. Most students here they put fxn and here they put f prime xn, so that becomes very wrong. Why? Because fxn is already a constant value, so, and we know that when you differentiate a constant value you get 0. Therefore always don't put xn at this point of differentiating. So before we substitute, let's see marks for this slide. So b1 for this value, b1 for this value, b1 for conclusion, b1 for this derivative. So next is to substitute for fxn using this and f prime xn using that. So it is after this, quoting this formula, that you'll begin putting xn, 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 xn where there is x. So let's see how that is done. So I think we realize that this is xn plus 1 equal to xn minus. So here you substitute it with fx, but you put xn now. Here you put the value for f prime x, but you put xn. So note that here at this point you must put the n. So after substituting, next is to simplify until we get the required expression. So what you are going to do, the first thing to do is to get the LCM. LCM is this, so I'll put everything under one quotient by using that LCM. So this LCM divided by 1 multiplied by xn, I'll come up with this part. Then also LCM divided by this, it cancels, so when I multiply by this I'll come up with only that part. The next is to open brackets. Then after opening brackets I will collect like terms. Then from there I remember that in my required expression they want me to factorize out 2 and 3. So 2 is common in this numerator and 3 is common in this denominator. So when I factorize them out I'll come up with that. Next is to quote the formula as it was given, and basically that's what is required. So M1 for this substitution into the formula for NRM. This one is called for combining or getting the LCM, and this one is for expressing it in the required format. So that was part B Roman 1. Now we shall go to part B Roman 2. Roman 2 says use the formula in B Roman 1, so this should be Roman 1 above, with an initial approximation of x naught equal to negative 0.1. So in this case they have given us the initial approximation. So sometimes they can give you or sometimes they will not, and they specify the formula to use, or they will not give you and they also don't specify the formula to use. So we shall see all those parts. Now in this question we have started with the part where they give you where they specify the initial approximation for you to use. So use this initial approximation to find the root of the given equation correct to 2 decimal places. So this one is, this number of decimal places is what you use to get the tolerance. Remember, tolerance is the same as the formula for error in a single value, meaning that because it is 2 decimal places, then the tolerance will be 0.005. So what you are going to do, you are going to use this formula and substitute your start. Remember we said you repeat the process until you reach somewhere. So we shall use the tolerance to know where to stop. So this formula you have to know it, and we have given that x naught is equal to negative 0.5. So we shall come and substitute for xn. So we are told that the initial approximation is, we take it to be negative 0.5. So what we are going to do, that negative 0.5 will be substituted in the formula we have derived. So where there is x, shall be putting the negative 0.5, negative 0.5, negative 0.5, negative 0.5. So when you use the calculator, it will come up with negative 0.2381. So they want the accuracy to 2 decimal places, meaning that these values, before you get the accuracy, they should be got by adding 2 more decimal places. So 2 plus 2 is 4. That is why we are using 4 decimal places. The next, this value you have got is substituted where there is x, so that's why we are saying that you repeat the process using the same formula. But before you do that, remember we didn't specify where to stop. Now how do you know where to stop? Is by getting the difference between the two successive iterations and comparing them with the tolerance. So the tolerance, because they want two decimal places, the tolerance will be 0.005. Like I said, the formula for tolerance is similar to the one for error. Similar to the one we used under the topic of error, and it was 0.5 exponent negative k, where k is the number of decimal places. So in this case, after getting x1, we are going to subtract the 2. This minus this, but it should be magnitude to ignore the negatives, like we said. So this minus this is this, so you'll come up with 0.2619, and when you compare it with the tolerance, which is 0.005, you realize that this value is still greater than the tolerance. So that means that you have to continue with the iteration. So you're going to go to and get x2. So to get x2, you use x1 where there is x. So use x1 where there is x, and when you use the calculator, you'll come up with x2 as negative 0.1968. Then you also have to compare the difference between the two successive iterations with the tolerance, and this value will still be greater than the tolerance, meaning you have to proceed with the iteration. So I'll come and get x3. So to get x3, I use the value of x2 where there is x. And when I do that, I'll come up with negative 0.1958. Then after that, I'll compare the difference with the tolerance. Now this time round, the difference is 0.001 and the tolerance is 0.005. So this time round, the difference between two successive iterations is less than the tolerance. Now when it is less than the tolerance, that means you have to stop and round off the very last value of x to the required accuracy. So when I round off this to two decimal places, I'll come up with the root as negative 0.20. So this is what we call a better approximation of the root. So, and that is how we use Newton-Raphson method. So basically that's what they wanted. Now let's see how marks can be awarded. So M1 for this substitution, B1 for the output, B1 for this output, B1 for this output, B1 for the root correct to two decimal places. So before we go to the next slide, I want you to realize that we are not awarding a mark for getting this difference between two successive iterations and comparing them with the tolerance. So these ones, there's no mark is awarded for them. What does that mean? It means that they can be bypassed. In other words, even if you don't show them in your working, you'll still get all the marks. Now the question is, if you don't show them in the working, how will you know where to stop? That can be known by sight. For example, you compare two successive iterations, then round off to the required accuracy. If I round off this to two decimal places, it will be negative 0.50, and this one to be negative 0.24. Now if they are the same, you stop. If they are not the same, you don't stop. Now because this is negative 0.50 and this is negative 0.24, it means that they are not the same, so you have to proceed. Then you go on to the second iteration. Then after getting the second iteration, you compare now this with this, the successive ones. When I round off this, it is negative 0.24, and this one will be negative 0.20. So they are still not the same, meaning you have to proceed. So you go on to x3. So this is supposed to be x3. So you're going on to x3. When I go to x3, I'll now compare x2 and x3. Now when I round off these to two decimal places, it is negative 0.20, and this one two decimal places, it is negative 0.20. Now these are the same when rounded off to the required accuracy. You know that word, required accuracy. Now because they are the same, it implies that that is why you stop, and this last value of x is what you round off and get this output. So that means that you can do your working without these steps of tolerance. Therefore, because of that, in the preceding questions we are not going to be adding these tolerances. We shall just be using sight to know where to stop. So that was question 1. Now we shall go to question 2, which came from UNEB 2019, paper 2, question 11, and says part A, show that the equation this has a root between 2 and 3. So let's first do that one first. So that's I rearrange, then that will be your fx. Then from there, physical substitution, substitute A2, come up with this. Because there is a trig function, the calculator should be in radians. Then substitute for 3, you'll come up with this. So there is a change of sign, therefore you can conclude that since this is less than 0, then there is a root between 2 and 3. So basically that was part A. Now shall go to part B, which says that show that the Newton-Raphson iterative formula for estimating the root of the equation in A is given by this formula, where n starts from 0 onwards. Hence, find the root of the equation correct to 2 decimal places. So this what 2 decimal places is what helps us to get the tolerance. Therefore, the tolerance will be 0.005. So let's also do part B. So for part B, the first thing to do is to get the derivative. So this is fx. So when I differentiate x, I'll come up with 1. When I differentiate 3 sine x, I'll come up with 3 cos x. The next is to quote the formula for Newton-Raphson. Remember, the formula has to be quoted. So before I go to the next slide, let's see how marks for this slide can be got. So B1 for this, B1 for this. Physical substitution needs to be seen. So because some students, they use a calculator and they just say F2 is equal to this. That will be wrong, so you will have lost all these marks. So B1 for conclusion, B1 for this derivative. So next is to substitute for fx and f prime x. So when I substitute this, what I'll get, then I'll simplify because they told us to prove. So I have to simplify it by getting the LCM, then expand and correct like terms, and then you express it in the required format. So basically that is what they wanted in the part of showing. Now we shall go to the hence part. So before we go to the next hence part, M1 is for this substitution, M1 for combining into one quotient or getting LCM, and B1 for expressing in the required format. Now for the hence part, in this case they didn't specify the initial approximation, and also they didn't specify the method to use. So what does that mean? It means that we are going to use to get the initial approximation by sight. So what do they mean by sight? By sight, you go back to your proof, because they told you that the root is between 2 and 3. So when I go back to this proof, f2 is negative 0.7279 and f3 is 2.5766. So you ask yourself, of these two values, which one is closer to 0? You realize that f2 is closer to 0, implying that the root is closer to x equal to 2, but not x equal to 2. Therefore, you pick values which are closer to 2. So you can pick either 2.1 or 2.2. If it was closer to 3, you would pick either 2.8 or 2.9. In other words, so in this case it is closer to 2, so we shall say we shall either pick 2.1 or 2.2. So any of the two is okay. That is when they don't specify the method to use. So shall come here and substitute for x naught to get our x1. Then after x1 you'll compare. Remember we said we are no longer going to use the tolerance, we are going to use the site. So this one to 2 decimal places is 2.20 and this one to 2 decimal places is 2.28. So they are not the same, implying that you have to repeat the process. When I repeat, I'll use this one to be able to get my x2, and that will be the value of x2. So when you compare x1 and x2, round off these to 2 decimal places, it will be 2.28, and round off these to 2 decimal places, it will be 2.28. So what does that mean? It means that they are the same values, so we have to stop and conclude that the root is 2.28 to 2 decimal places. So basically that's what they wanted. Now let's see how marks can be awarded. So B1 for stating the value of x0 can be either 2.2 or 2.1. Then this one for substitution, this for output, this for output, this for conclusion. So that was question 2. Now we shall go to question 3, which came from UNEB 1999 paper 2, question 12, and says part A, show that the iterative formula for approximating the root fx equal to 0 based on Newton-Raphson process for the equation this is that. So let's start with that part. So we know that fx is that. So the first thing to do is to differentiate. So when I differentiate this one, this is a product. So we use product formula, keep this one constant, and differentiate this to come up with this. Then plus, keep this one constant, and differentiate this to come up with 1. So 1 times that is the same as ex. Then differentiate this to come up with 5. Differentiate this to come up with 0. So next is to quote the formula, and after quoting the formula you substitute. Now because they wanted you to prove, you have to simplify and get the required expression. So combine by getting LCM into one quotient, then open brackets for the numerator, and then collect like terms for the numerator, and that is the required expression. So B1 for derivative, M1 for substitution, M1 for combining into one quotient, and B1 for the required expression. So that was Roman 1. Roman 2, show that the root of the equation in Roman 1 above lies between 1 and 2. Then hence find the root of the equation, correct your answer to 2 decimal places. So showing, you have to use physical substitution. So first of all, our fx is that. Therefore, I'll come and substitute for x equal to 1 and also for x equal to 2. There is a change of sign. Therefore, I'll conclude that since this is less or equal to 0, is less than 0, it implies that there is a root between 1 and 2. So for the hence part, they didn't specify the initial approximation, and also they didn't specify the method, so we are going to use site. So by site, if you look at this f1 and this one, it is this value which is closer to 0, meaning that the root is closer to x equal to 1. So I can either use 1.1 or 1.2. If it was closer to x equal to 2, I would use 1.8 or 1.9. So in this case, I'll choose one of the two. So let me choose 1.2. If I choose 1.2, I'll substitute to come up with that value. Then I will use site to compare. So this one to 2 decimal places, it is 1.20, and this one to 2 decimal places, it is 1.20. So they are the same values, meaning that you stop there and you conclude that the root is 1.20 to 2 decimal places. So basically that's what they wanted. Now let's see how marks can be awarded. So M1 for this physical substitution, B1 for the output, B1 for the output, B1 for conclusion, B1 for this value of x naught, m1 for the substitution, b1 for output, b1 for root to the required accuracy. So that was the part of Newton-Raphson method. Now we shall go to, remember I told you in Newton-Raphson method they can either specify the formula to use to get the initial approximation, or they don't specify. Now in this part, in the previous part we have dealt when they don't specify and also when they give you the initial approximation. So in this part we are going to deal with when they specify that you have to use linear interpolation to get the initial approximation. So if a function f(x) equal to 0 has a real root between x equal to a and x equal to b, the initial approximation x naught of this root can be obtained using linear interpolation method. And this is based on the fact that f(x naught) is equal to 0. Therefore, for a better approximation, the process of interpolation is repeated until the difference between the two successive values is less than the tolerance. So I think we saw this. We have under Newton-Raphson method, you can either use this method approach or use the method approach of sight. Now that means that interpolation can be used to get the initial approximation using this knowledge, or to get the better approximation by using this knowledge, whereby you have to repeat the interpolation process until this value is less than the tolerance. So we are going to see both parts, how linear interpolation can be used when they want only to use it to get initial approximation, and also when they want you to use it to get a better approximation. So we shall start with question 1, which came from UNEB 1993, paper 2, question 1, and says, show that the equation this has a real root between x equal to 1 and x equal to 2. So I think let's start with that. So fx is that, therefore physical substitution is needed, so f1 is that and f2 is that. So there is a change of sign, therefore you shall come and conclude that since the product is less than 0, then there is a root between 1 and 2. So we have done with showing. Now let's go to the next part. So the next part says, Roman 1, using linear interpolation, find the first approximation of this root. So we have to remember the knowledge that when you are getting the initial approximation, fx naught is equal to 0. So that knowledge shall come here and do the tabulation. Tabulate values of x and fx. So these are the values of x and these are the values of fx. Now remember, when x is 1, fx is -1. Then when x is 2, fx is 21. Then when x is x naught, fx is 0. I think we saw that in the introduction part. So next is to use interpolation method. I believe by now you know the method. So when I make x naught the subject, x naught will be equal to 1.0455. So basically that's what they wanted. Now let's see how marks can be awarded. So B1 for this, B1 for this, B1 for this, B1 for this, M1 for that, A1 for that. So Roman 2 said, using Newton-Raphson formula twice, find the value of this root correct to 2 decimal places. So here they specified the number of iterations. So come on, first get the derivative of fx, then we quote the formula for Newton-Raphson, and after that we shall substitute. Now here they didn't want us to prove, meaning that we stop at substituting, then we start putting our values. So x naught is that, then implying that x1 will be got by substituting for x naught, which is 1.0940, but they told us use it twice, so we have to use it the second time to come up with the second value of x, which is 1.0921. So after that we shall conclude that the root is 1.09 to 2 decimal places. So basically that's what they wanted. Now let's see how much can be awarded. B1 for derivative, M1 for substitution, this M1 for this substitution, B1 for output, B1 for output, B1 for conclusion. So that was question 1. Now we shall go to question 2, which came from UNEB 2006, paper 2, question 14b, and say that show that one of the roots of the equation this lies between 2 and 3, and by use of linear interpolation find the root to 2 decimal places. So here it means that they want you to use linear interpolation to get a better approximation. So when they specify the number of decimal places, they want a better approximation of the root. So let's start with showing. So here fx is that, therefore we are going to use physical substitution. When x is 2, you come and substitute, and also when x is 3, you come and substitute. There is a change of sign, therefore you can conclude that since this product is less than 0, there is a root between 2 and 3. So that is the part of showing. B1 for that, B1 for that, B1 for this. Next we are going to go to linear interpolation method to get a better approximation. That word, better approximation. So the first extract are the values we have of F1 and F2. F2 and F3. So F2 is -1, F3 is 1, fx naught is 0. So by linear interpolation, we shall be able to come up with x naught as 2.5. After that, we have to get the corresponding value of f2.5, which will be 0.25. Now after that, we are going to compare this f of 0.25 and these values. So if you compare it with this is negative, so you compare it with the negative value, and you realize that this value is closer to 0 than -1. So what does that mean? It means that we are going to remove this and replace it with this, and that will be our second extract. So we have replaced this f2 with f2.5 to get x1. Therefore we shall still use linear interpolation to come up with the value of x being equal to 2.6. Then also get f2.6. f2.6 is -0.04, so it is closer to 0 than this one. So we're going to replace this with this in the third extract. So before we go to the third extract, let's see marks for this slide. So M1 for this, B1 for that, and B1 for that. So now we shall go to the third extract, where I shall replace 2.5 with 2.6. Then I will still use linear interpolation to come up with the value of x2, which is 2.6154. Then I get f of that value, which will be -0.0059. So next we shall go to the fourth extract, where we shall replace this with these values. Then we shall still use linear interpolation to come up with the value of x3. Now remember, we are using sight to know where to stop. So if I use sight, this value to 2 decimal places is 2.62, and also this value to 2 decimal places is 2.62. Therefore I'll come and conclude that the root is 2.62 to 2 decimal places. So basically that's what they wanted, and B1 will be for this value and B1 for this value, B1 for conclusion. So that was question 2. Now we shall go to question 3, which came from UNEB 2002, paper 2, question 5, and says, use a suitable table of values to show that the function this has two real roots in the interval of -3 to +3, and hence use linear interpolation to determine the approximate value of the negative root of the function, giving your answer to 1 decimal place. So first of all, you should remember that when it's in this form, it implies that this is fx, so fx is that. Therefore, we shall tabulate our values using this interval, and we shall be able to come up with when x is -3, fx is that. When x is -2, fx is that. When x is -1, fx is that. When x is 0, fx is that. -infinity, when x is 1, fx is that. And when x is 2, fx is that. When x is 3, fx is that. So that they told us to show that use suitable table to show that there are two real roots. So we shall look for two sign changes. The first one is this from your tier, that we shall come and conclude that there's a root between -2 and -1. Then the second one is from your tier, meaning there's a root between 1 and 2. So B1 will be for the table values, and B1 for the first root, B1 for the second root, locating them. So next is to use linear interpolation. Now here they didn't specify whether it is initial approximation or beta approximation. So what does that mean? It means that when they don't specify whether it's initial or beta, but they give the required accuracy, it is automatic that they want a beta approximation. So for the negative root, we shall come up with the first extract of the values which give the negative, where the negative root lies, and then we use linear interpolation to come up with that value of x0, which is that. Because they want it to 1 decimal place, that's why we add 2 more decimal places to get 3 decimal places there. Then fx of that, it will be that. Now next is to use these two values to replace these values with this one to come up with the second extract. So after that, we shall use linear interpolation to come up with the value of x1, and therefore when I make x1 the subject, x1 will be -1.677. So when I compare this to 1 decimal point is -1.6, and this one to 1 decimal point it is -1.7. Therefore I have to continue. So I have to get my value of fx, which is that. Therefore I'll replace this with this positive value. Before that, let me see the marks for this slide. So M1 for substitution, B1 for output, B1 for x1. So when I replace, I'll come up with the third extract. And use linear interpolation to come up with the value of x2. And the value of x2, and therefore, when I compare this with the first one, the x1 to 1 decimal point, it was -1.7, and also this one to 1 decimal point is -1.7. Therefore the root is -1.7 to 1 decimal point. So B1 for x2, B1 for the required root. So that was the method when they specify that they want you to get the initial approximation using interpolation, or beta approximation using interpolation. But sometimes they can specify that they want you to get the initial approximation using a graph. and this graph is split into two, they can tell you to draw a single graph plot. Single graph plot means that you have only one function. Then two graph plot means that you have two functions. So they can specify that you use a single graph or two graphs. So when they specify that you use a single graph, how do you answer such? So in this method, a table of values of that very function is drawn, and a graph of y equal to fx is plotted for a given interval of values of x. The initial approximation of the real root of this is the value of x, where the graph cuts the x-axis. In other words, it is the x-intercept. So if it is one graph, always remember that the x-intercept will be the initial approximation of the root. So you shall use that knowledge to go through this question. So question 1 came from UNEB, paper 2, UNEB of 2019, paper 2, question 3, and says, show by means of a graph that the equation this has only one real root that lies between a half and 1. So the first thing to do is to get our fx. So rearrange, put everything on one side, and that will be your fx. So fx will be this, y equal to x plus ln x minus 0.5, because log base e is the same as natural log. Therefore, I'm going to tabulate my values of x and y. So x and y, when x is 0.5, I'll come up with that, because I'll come up with negative this. So we use a maximum of 2 decimal places because those are the a maximum of 2 decimal places can be plottable. But if you use 4 decimal places, that value cannot be plotted, therefore it will be wrong. So tabulating values to plot on a graph, the maximum should be 2 decimal places and the minimum is 1 decimal point. Don't use whole numbers. So when x is 0.6, y will be that. When x is 0.7, y will be that. When x is 0.8, y will be that. When x is 0.9, y will be that. And lastly, when x is 1, y will be that. So how do you know the range of values to use? What you should know is that you must use a minimum of 5 plottable values. So these are 1, 2, 3, 4, 5, 6, meaning that I'm safe. If you use 4 points, that will not be okay. So it should be a minimum of 5. So before we go to the next slide to plot the values, B1 will be for this, for tabulating the values. So next is to plot our graph to show graphically that there's a root between a half and 1. So a half and 1, what I want you to remember is that when they specify a half and 1, it means that the first value must be a half and the last value must be 1. Always remember that when they specify the range, don't go outside the given range. So you need a graph paper. Then on a graph paper, the first thing to do is to put your x-axis and the y-axis. Then you'll put the scale for the horizontal axis. After that, you also get the scale for the vertical axis. So after that, you are going to plot the values. So you are going to plot values of x, y with x. So when x is 0.5, you plot this. When x is 0.6, you plot this. When x is 0.7, you plot this. When x is 0.8, y is that. When x is 0.9, y is that. And when x is 1, y is that. So you shall come and plot that. So when x is 0.5, that is the value of y. When x is 1, that's the value. When x is 0.6, 0.7, that's the value. 0.8, 0.9, 1. So next is to draw a smooth curve through all these points. So let's do that. The curve must be reasonably smooth and passing through all the points. Then now that we have to label our graph. Then we remember that the root is the x-intercept. So we shall come and say that the root is that. And after that we shall conclude that since there is only one intercept, it implies that the equation has only one real root in this interval. So basically that's what they wanted. Now let's see how much can be awarded. So B1 for axes, B1 for plotting points correctly, B1 for the reasonably smooth curve, B1 for locating the root, and concluding. So that was question 1. Now we shall go to question 2, which says show graphically that the equation this has a real root between 0 and -1, and hence use Newton-Raphson method to find the root of the equation corrected to decimal places. So first we shall tabulate our values of x and y. So when x is -1, we shall come up with y as that, negative 0.8, we shall come up with that, negative 0.6, we shall come up with that, negative 0.4, we shall come up with that, negative 0.2, we shall come up with that, and lastly 0, we shall come up with that. So B1 for that. The next is to, they told you to show graphically, so we have to plot. Therefore we shall come and get our graph paper, then put the axes, x-axis and y-axis, then put the scale for the horizontal axis, and then the scale for the vertical axis, then we start plotting. When x is -1, the y value is that, negative 0.8, y value is that, negative 0.6, y value is that, negative 0.4, y value is that, negative 0.2, y value is that, and lastly 0, y value is that. So next is to draw a smooth curve through all these points. So when you do that, you shall come up with that. The curve must be reasonably smooth, and it has to be labeled. Then remember that the intercept, x-intercept, is our root. Therefore we shall come and conclude that since the curve cuts the x-axis in the interval that, it implies that there is a root between -1 and 0. So basically that's what they wanted in the part of showing. So let's see marks, how they can be awarded. So B1 for both axes, B2 for plotting all points correctly, B1 for smooth curve, B1 for stating the initial root, and also concluding. So next they wanted you to use, now we have got the initial approximation, we have to use Newton-Raphson. So Newton-Raphson, the first thing to do is to differentiate the function to come up with this. Then you quote the formula for NRM or Newton-Raphson method, then you substitute. So now here they didn't tell you to prove, so you stop at only the part of substituting into the formula. Then you go to the initial approximation, which was got from the graph as negative 0.68. Therefore when I substitute, I'll be able to get my value of x1, and x1 will be negative 0.6755. Now when I compare these two decimal places, negative 0.68, and also this one is negative 0.68, meaning that you stop there and conclude that the root is negative 0.68. So basically that's what they wanted. Now let's see how much can be awarded. So B1 for the derivative, M1 for substitution, M1 for this part, M1 for this part, B1 for the output, B1 for the required root. So now shall go to question 3. Question 3 part A says, show graphically that the equation this has a real root between 0 and 2. So you have to plot the graph, but before that we have to first tabulate our values. Therefore the y value will be this because this is our function, so we shall tabulate values of x and y. But those values of x and y must range from 0 up to 2. So when x is 1, y is that. When x is 2.5, y is that. When x is 0.5, y is that. When x is that 0.75, y is that. When x is 1, y is that. When x is 1.5, y is that. When x is 1.5, y is that. When x is 1.75, y is that. And lastly, when x is 2, y is that. So the question is, why did I use 0.25? It is because if, for example, I use 0.1, there will be very many values because I have to put 0.1, 2, 3, 4, 5, so there will be 20 points to plot, which is too much. But remember, in our case, we need a minimum of 5. As long as they are 5 points, you are good to go. Now, if I use 0.2, there will be 10 points. And if I use 0.5 to make it smaller, there will be 1, 2, 3, 4, 5. So 0.5 is okay. Then to make it more smoother, I can add in other points, so 0.25, 0.75, like that, to make it more smooth. B1 will be for now tabulating these values. So next is to plot our graph. So there we need our graph paper. Then on the graph paper we shall plot the x and y axis. Then we shall demarcate the scale for the x-axis. Then also the scale for the y-axis. After that, we shall now start plotting. So plotting when x is 0, that is the point. When x is 0.25, that's the point. 0.5, that is the point. 0.75, that is the point. 1, that is the point. 1.25, that is the point. 1.5, that is the point. 1.75, and also 2. So next is to draw a smooth curve through all these points. So let's do that. We have to also label the curve. All that, remember that the x-intercept is our root. Therefore, we shall come and conclude that since the graph casts the x-axis in the interval from 0 to 2, it implies that there is a root between x equal to 0 and x equal to 2. So basically that's what they wanted in part A. Now let's see how much can be awarded. So B1 for the axis, B2 for plotting, B1 for reasonable smooth curve, B1 for stating the initial root and also conclusion. So part B says that derive the iterative formula based on Newton-Raphson method that can be used to find a better approximation to the root. Hence find the root correct to 3 decimal places. First of all, we have to differentiate fx to come up with that. So differentiate x sine x. Now this is the product, meaning that what you are going to do, first keep x the constant, then differentiate sine x to come up with cos x, then keep sine x the constant and differentiate x to come up with 1. Then when I differentiate 1, I come up with 0. The next is to code the formula for Newton-Raphson method and substitute. To substitute for fx and f prime x, but this time there is xn. So after that, since they didn't tell us to show or to prove, we have stop at substituting and we go to our hence part. So x naught, we got it from the graph and it was 1.08. Therefore we shall use it to get x1, which is that. Then we use x1 to get x2. Why? Because the answer to 3 decimal places. Now this one to 3 decimal places is 1.080 and this one is 1.114. They are not the same, so you have to go to the second iteration. So the second iteration, if you compare this one, x1, it is 1.114 and this one is also 1.114. So you stop there and say that the root is 1.114 to 3 decimal places. So basically that's what they wanted. Now let's see how marks can be awarded. So B1 for differentiating, M1 for substitution, M1 for the substitution, B1 for the output, B1 for the output, B1 for the conclusion. So now that was using a single graph. What about 2 graph plots? So 2 graph plot, they give you 2 graphs and you plot the 2 graphs on the same axis. Then after that you look for the intersection. So the point of intersection, the x value of the point of intersection of the 2 graphs is what becomes the initial approximation of the root of fx equal to 0. So that is the only difference between single graph plot and 2 graph plot. Single graph plot, it is the x-intercept, and 2 graph plot, it is the point of intersection. So with that knowledge, you shall go through question 1. Question 1 came from UNEB 2020, paper 2, question 14, and part A, Roman 1 says, draw on the same axis the graphs of y equal to x sine x and y equal to ex minus 2 for the interval 0.5 to 1.5. So the first thing to do is to tabulate the values of both curves. So we shall have a column, a row of x, a row of one function which is x sine x, another function which is ex minus 2. So when x is 0.5, this one gives me that and this one gives me that. When x is 0.7, I'll come up with that and that. When x is 0.9, I'll come up with that and that. When x is 1.1, I'll come up with that and that. When x is 1.3, I'll come up with that and that. When x is 1.5, I'll come up with that and that. So I think realize that we are starting from this 0.5 and ending at 1.5. So if you exceed this range, then you are off track. So make sure you don't exceed that range. It has to be from the given range, which is from 0.5 to 1.5. After that we shall plot. Now plotting, you need a graph paper. On the graph paper you will put the x-axis and y-axis, and the axis should be labeled. Then next is to put the scale for the horizontal axis. Then we shall also put a scale for the vertical axis. Then next is now to plot. Now we shall start with one graph, plot it to the fullness, and then go to the second graph. So if we start with the first graph, the first value is 0.24, so we plot it there. The next value is 0.45. The next value is 0.70. Next value is 0.98. Next value is 1.25. And lastly 1.5. So we have to draw a smooth curve through all these points. So let's do that. Then we have to label the graph that is y equal to x sine x. Then next we shall go to the second graph. When 0.5, the first value is negative 0.35, which is that. Next value is 0.01. Next value is 0.46. Next value is 0.1. Next value is 0.67, and lastly 2.48. So we shall also draw a smooth curve which is reasonably smooth through all those points. So let's do that. We have to also label the graph. Then, like we said, for the two graph plot, you look for the point of intersection, and the x value of that point is what becomes the root. So basically that's what they wanted. Now let's see how much can be awarded. So B1 for this, B1 for that, B1 for the axis, B1 for plotting and drawing this one, B1 for plotting and drawing this one, B1 for stating the root. So Roman 2 says use your graph to find an approximate root of the equation. You have already seen it. It is this value, which is 1.08. Note that we're using the approximation sign. Then part B says using Newton-Raphson iterative formula and your approximate root in A above as the initial value, calculate the root of the given equation. So this was supposed to be given equation, correct to 3 decimal places. So the first thing to do is to differentiate. When I differentiate, this one is 0, then this one is negative ex. Now this one is a product. What you're going to do, keep this one constant, differentiate this to give you that. Then after that you say plus, keep this one constant, differentiate this to give you 1. Then from there we shall quote the formula for Newton-Raphson method and substitute for fx and f prime x. Since they didn't tell you how to derive, we shall just substitute now. So sub x naught was got from the graph, so we shall come and substitute for x naught to come up with the value of x1. Then I round off to 3 decimal places. This is 1.080, this is 1.085, so they are not the same. That means I have to continue, use x1 to get x2. I'll come up with 1.08508. So when I round off, this one is 1.085, this is 1.085 to 3 decimal places, meaning that they are the same, therefore the root will be 1.085 to 3 decimal places. So basically that is what they wanted. So B1 for this derivative, M1 for substitution, M1 for this substitution, B1 for the output, B1 for this output, B1 for the conclusion. So that was question 1. Now we shall go to question 2, which came from UNEB 2018 paper 2 question 14, and says part A, draw on the same axis the graphs of this and this for this range. So let's first do that. The first thing to do is to tabulate. So I'll come and tabulate for both values, for both curves. So x, then put there this curve, then also this curve. So they give us the range from 2 to 5. So when x is 2, we shall come up with that and that. When x is 2.5, we shall come up with that and that. When x is 3, we shall come up with that and that. When x is 3.5, we shall come up with that and that. When x is 4.0, we shall come up with that and that. When x is 4.5, we shall come up with that and that. When x is 5, we shall come up with that and that. So note that we don't exceed the given range. Don't exceed the given range. So B1 for both values. There should be a minimum of 5 points. So now that we have tabulated our values, we shall go and plot our two graphs. So the first thing we need is our graph paper. Then we shall draw the axes, x-axis and the y-axis, and label them. Then from there we shall put the scale for the horizontal axis. Then after that we shall put the scale for the vertical axis. Then from there we shall start to plot. So I'm going to start with one curve. So we shall start with this one of 2 minus ex, which has these values. So I'll come and say when x is 2, I'll come up with that value. 2.5, I'll come up with that. 3, I'll come up with that. 3.5, I'll come up with that. 4, I'll come up with that. 4.5, I'll come up with that. 5, I'll come up with that. So next is to draw a smooth curve, reasonably smooth through all those points. So let's do that. After that I have to label the curve. So next is to plot now the second curve of y equal to root x using these values. So I'll come and say when x is 2, I'll come up with that value. 2.5, I'll come up with that. 3, I'll come up with that. 3.5, I'll come up with that. 4, I'll come up with that. 4.5, I'll come up with that. 5, I'll come up with that. So next is to draw a smooth curve through all these points. So let's do that. And I have to label the graph. So next I remember that the intersection is our root. So I'll come and look for that point, read off that value, and that will be the required root. Therefore the initial approximation is this. So this one shows how to get it. For example, how is it got? The first thing to do, you'll come and we want to read off this value. So first look at this this value which is plotted and is 3.5. Then after that you'll come and count the small squares from here up to the root, and those will be 8.5. Then after that you remember the scale for one small square. One small square is got by saying 4 minus this, which is 0.5, divided by the number of small squares, which are 10, to come up with 0.05. So we'll end up with a value of 3.925. Therefore, from the graph, the root lies between 3.5 and 4. So now we shall go to the hence part. So for the hence part, in this question, they say that hence use Newton-Raphson method to find the root of the equation correct to 3 decimal places. So the first thing to do is to get the derivative of fx. So derivative of fx, if I differentiate this, I'll come up with negative ex in negative x. Differentiate root x, I'll come up with 1 over 2 root x. Then differentiate 2, I'll come up with 0. When I put them under one LCM, it will become that. So before I go to the next slide, let's see marks for this slide. So B1 for the axes were labeled B1 for plotting, and for plotting all the points for this curve, and also another B1 for joining using a reasonably smooth curve. B1 for plotting points of this curve, and B1 for joining to get a reasonably smooth curve. B1 for stating the root and also concluding. B1 for the derivative. So now that you have got the derivative, we can come and quote the Newton-Raphson formula and substitute. So when I substitute, I'll come up with that. And since they didn't tell us to derive, we shall just stop there and begin using the values. So we shall start with x naught. X naught was got from the graph, and it was 3.925. So when I substitute for x naught, I'll come up with that value, and the value of x1 will be 3.92112. So remember, they want the accuracy to 3 decimal places. That's why we add 2 more to get 5 decimal places. So rounding off to 3 decimal places, this is 3.925, and this will be 3.921. So they are not the same, meaning you have to continue. So when I use x1 to get x2, I'll come up with that, and the value of x2 will be 3.9211. So this to 3 decimal places, it is 3.921, and this one is also 3.921, meaning that you stop there and conclude that the root is 3.921 to 3 decimal places. So basically that's what they wanted. Now let's see how much can be awarded. So M1 for this substitution, B1 for this value, B1 for this value, B1 for conclusion. So that was question 2. Now we shall go to question 3, which came from UNEB 2017 paper 2 question 14, and says, by plotting graphs of this and this on the same axis, show that the root of the equation this lies between 2 and 3. So let's first start with that. So the first thing to do is to tabulate the values of y equal to x and y equal to 4 sine x. So we shall put x for y equal to x and 4 sine x for y equal to 4 sine x. Then when x is 2, remember we have to use this range. So when x is 2, 4 sine x is this. When x is 2.2, here we shall get that. When x is 2.4, here we shall get that. And when x is 2.6, here we shall get that. When x is 2.8, here we shall get that. When x is 3, here we shall get that. So this type of value, that is 1 mark. So next is to plot our graph. So to plot, you need a graph paper. So let's first get a graph paper. So after getting the graph paper, you need to show the label the axes x and y axis. Then after that, we shall put the scale for the horizontal axis. Then we shall put the scale for the vertical axis. So next is now to plot our curves. So when you look at this one, y equal to x is a straight line. So what does that mean? A straight line, we only need two extreme points. So we shall plot for this and this. So we shall plot a point of 2, 2 and a point of 3, 3 for this line of y equal to x. So let's first do that. So when x is 2, y is also 2, and when x is 3, y is also 3. So we have to use a ruler now to join these 2 points. So when you use a ruler, we shall come up with that. And then we label the line. So next is for this other curve of y equal to 4 sine x, and these are the values, so we have to plot all of them. Therefore, shall come here and say when x is 2, y is that. When x is 2.2, y is that. 2.4, y is that. 2.6, y is that. 2.8, y is that. 3, y is that. So now this is not a straight line, so we have to use freehand to draw a smooth curve through all these points. So let's do that. Then we also have to label. After that, we shall remember that the point of intersection gives the root. So the root will be 2.47. And therefore we shall come and conclude that since the two graphs intersect in the interval this, it implies that there is a root between x equal to 2 and x equal to 3. So basically that's what they wanted. Now let's see how marks can be awarded. So B1 for labeling axes, this B1 for plotting the points of this line, and B1 for joining using a ruler, B1 for plotting, B1 for joining using a smooth curve, B1 for stating this and making this conclusion. So now we shall go to the hence part. For the hence part, they said use Newton-Raphson method to find the root of the equation correct to 3 decimal places. So first thing to do is to differentiate. When I differentiate x, I'll come up with 1. Differentiate 4 sine x, I'll come up with 4 cos x. Then I'll quote the formula for Newton-Raphson and then substitute. Then I remember that my initial approximation from the graph was 2.47, so I'll come and substitute to come up with the value of x1, which is 2.47458. Now when I compare this one to 3 decimal places, it is 2.470, and this one is 2.475. Therefore, they are not the same, so we have to proceed. So use x1 and get x2. Remember, calculator should be in radians. So that gives me this. Therefore, to 3 decimal places, this is 2.475, and this is also 2.475, meaning we stop there and conclude that the root is 2.475 to 3 decimal places. So basically that is what they wanted. Now let's see how marks can be awarded. So B1 for this derivative, M1 for substitution, B1 for x1, B1 for x2, B1 for conclusion. So that has been Newton-Raphson method. Now we shall go to the reverse of Newton-Raphson formula. Sometimes they can give you a formula and ask you to identify the equation which was used to get that Newton-Raphson formula. So in this case, that is where the word reverse of Newton-Raphson formula comes in. So let's start with question 1. Question 1 says, determine the equation being solved using the iterative formula this. So that means that you have to work backwards. So backwards, how do you do that? So that's the equation which was given. Next is to remember a certain concept that as n tends to infinity, n is the number of iterations, then xn tends to x, where x is the root. So what does that mean? It means that instead of writing xn plus 1, xn, we shall replace it with the root, which is x. So when we come, we shall get that. Next is to cross multiply and collect like terms. So when I cross multiply, collect like terms, I'll come up with that. Put everything on one side, it will be that. Therefore, the function or the equation being solved is this. So basically, that's how you do such a question. So B1 for this condition, M1 for replacing, M1 for cross multiplying, M1 for putting all terms on one side and stating the equation. Then that was question 1. Now we shall go to question 2. Says that given the formula this, find the equation whose root is sought. Hence show that the equation has 3 real roots. So still we shall first code the condition as n tends to infinity, then you come and replace and cube, then cross multiply, and that will be the equation. So before we go to the next slide, B1 for starting this condition, M1 for replacing, M1 for cubing, M1 for putting all terms on one side, and this is the this is the required equation, and this is fx. Fx will be used to get this other part. So like we always did, we have to tabulate, then we locate. So when x is -3, fx is that. When x is -2, fx is that. When x is -1, fx is that. When x is 0, fx is that. When x is 1, fx is that. When x is 2, fx is that. And when x is 3, fx is that. Then we shall identify that there is a change from here to here, meaning that there is a root between -1 and 0. Then also there is a change of sign from here to here, meaning that there is a root between 0 and 1. Also a change of sign from here to here, meaning there is a root between 1 and 2. So hence that is what they wanted. So let's see how marks can be awarded. So B1 for that table values, B1 for this, B1 for this, B1 for that. So now we shall go to general form iterative formula. So what we have been dealing with is Newton-Raphson method. Now we need to look at what we call general form iterative formula. So this method can only be used, like I said, for polynomials and cannot be used for transcendental equations like equations having exponentials, natural logs, and trigonometric functions. This method cannot be used. So polynomial must be of single variable. For example, this will be a polynomial. So if I consider this polynomial, in this polynomial the variable is x, and the iterative formula is got by rearranging to make x, which is the variable, the subject, using any approach. And since there are many ways in which the original polynomial can be rearranged so that x is made the subject, it implies that more than one iterative formula can be obtained as shown below. So this part of general form iterative formula, it is not only, you don't only get one formula, you get a number of formulae, and therefore you have to identify which one is most suitable. So you shall also see how to identify which of the formulae you have got is most suitable. Now how is it got? You look for ways of here, for example, there are two x's. Now you should look for a way of making one x the subject and the others will go on the other side. So let's first see how that is done. So in the first case, I can choose to say, let me put this x this side and I get that. So in this way I've made one x the subject and the others are on the other side, meaning that therefore I can come and say that the first iterative formula will be that, So that basically as simple as that. So that is how they get general form iterative formula. Make one x the subject, put the rest on the other side. So that is when I've made this x the subject. What if I choose to first make this x cube the subject? I will have to divide throughout by, I have to get the cube root of x of e on both sides. So when I get the cube root on both sides, this x cubed will become x and this one will become x plus 1 to power a third. Now when I do that, it means that the second iterative formula is equal to this. So as simple as that. So that is how they get general form iterative formula. You just look for a way of making one x the subject and put all the rest of the terms the other side. So in this case, now next I can also choose to first divide throughout by x squared. When I divide throughout by x squared, I'll come up with that. Therefore, that means that the third iterative formula will be that. As simple as that. But also, I can choose to divide throughout by x. So that means that I'll come up with this. And when I put a square from both sides, I'll come up with that. Therefore, the general form iterative formula will be that. As simple as that. So that is how they get these general form iterative formula. So as long as they don't specify that it is Newton-Raphson and it's a polynomial, you can use this. As long as you see the word general form iterative formula, as we shall see in the examples. So question 1 says, part A, by plotting graphs of this and this on the same axis, find the least positive root of the equation this correct to 1 decimal point. Then part B, they said, show that the iterative formula for solving this equation is this. I think you realize that here they just said iterative formula, and also this is a polynomial, meaning you can use the method of general form iterative formula. So let's first do part A and we'll see how part B is done. So for part A, you need to tabulate first, like we have always done. So when I tabulate, I'll tabulate for this one x cubed and also for this one 3x plus 12. So when x is 0, 0, x cubed will be that and that will be that. Then 0.5, when x is 0.5, I'll come up with that. Why? Because this is a straight line. Now a straight line, you only need 2 points. So we are going to get this point and also the very last point. So in between there, you don't need any point. That is why I'm ignoring them. So when x is 1, I'll come up with that. When x is 1.5, I'll come up with that. And when x is 2, I'll come up with that. When x is 2.5, I'll come up with that. When x is 3, I'll come up with that. And also that. So we are going now to plot these points. The first thing we need is a graph paper. Then next we have to draw the axes, x-axis and the y-axis, and label them. Then we have to get the scale for the horizontal axis. After that, we have to get the scale for the vertical axis. So now we are going to plot both the curve and the line. So if we start with the curve, we have to plot these values. So let's start by doing that. So the first one, when x is 0, y is all that. When x is this, 0.5, y is that. When x is 1, y is that. When x is 1.5, y is that. When x is 2, y is that. When x is 2.5, y is that. When x is 3, y is that. So next is to draw a smooth curve, reasonably smooth, through all these points. So let's do that. And also label the curve. After that, we shall also plot for this other curve, actually a straight line. So we need these 2 points, 12 and 21. So you come and plot when x is 0, y is that, when x is 3, y is that. So we need a ruler and draw a straight line joining those 2 points. Let's do that, and also label the line. So now we shall remember that the intersection is what gives us the root. So we shall look for that x value of the point of intersection, and the root will be 2.7. Remember, they want the value to 1 decimal point. So basically that's what they wanted. Now let's see how marks can be awarded. So B1 for the axes, B1 for drawing the points, and B1 for joining using a ruler, B1 for plotting, B1 for joining using a smooth curve, B1 for stating the root to the given accuracy. So that was part A. Therefore now we shall go to part B. So part B, they said show that the iterative formula for solving the equation this is that. So that is a given equation. What you're going to do, we are going to make x cubed the subject, then we divide throughout by x to come up with that, then put square root on both sides to come up with the required iterative formula. Then part 2 said using the formula in B twice, find a better approximation to the root in A correct to 2 decimal places. So we shall come and substitute for x. So when x is 2.7, as we got previously, put it here, we shall come up with 2.7285. But remember, they told us to use it twice, so we have to also get x2 using this one here to come up with 2.7199. Therefore, we shall conclude that the root is 2.72 to 2 decimal places. So this one is for rearranging and dividing throughout by x, and B1 for the required expression, B1 for the value of x1, value of x2, required root. So now we shall go to testing suitability of an iterative formula. Like I said, since there are many formulas, it implies that you have to identify which one is most suitable. So there are 2 methods for identifying which of the 2 is most suitable. One is by analyzing the tolerance level, another one is by performing a derivative test. So we shall start with the tolerance level. So a suitable iterative formula is one whose values of the xn plus 1 tend to capital X as n tends to infinity, where x is the root of the polynomial. Such a formula is said to be convergent or suitable, since its successive values approximate successive approximations reduce to a constant value. This constant value is now the root of the polynomial or equation, otherwise it will be divergent and hence can't give a constant value or root. So if it is convergent, it is suitable; if it is divergent, it is unsuitable. Therefore, using the method of tolerance, it will converge if its tolerance goes on decreasing, otherwise it will be divergent. So with that, we shall go through question 1, which came from UNEB 2001, paper 2, question 11a, and says, given 2 iterative formulae, formula 1 and formula 2, which are these ones, taking x0 and taking x0 as 2.5, use each formula thrice to 2 decimal places to decide which is more suitable formula. Give a reason for your answer. So we shall start with formula 1 and substitute. They are giving us the initial approximation. So formula 1 is that, where therefore x0 is that, x1 will now be that, the tolerance value is that. Then x2 will now be that. They told us to use it thrice, so you have to use it thrice. x3 will also be that, and the tolerance will be that. So since the tolerance keeps on, I think I can see this one is small, from here to here it increases, from here to here it increases. So because it is increasing, it implies that it is divergent. So B1 for this first tolerance, B1 for the second tolerance, B1 for the third tolerance. Then now we shall go to formula 2. So for formula 2 still we shall do the same. X1 will be that, tolerance will be that, and X2 will be that, tolerance will be that, X3 will be that, and tolerance will be that. What does that mean? It means that I think we'll see here, from here to here it is reducing, and from here to here it is reducing. So since it is reducing, it implies that it is convergent. What does that mean? It means that formula 2 is more suitable since it gives convergent roots. So this is the reason. So B1 for this, B1 for this, B1 for that, B1 for the reason. So now we shall go to the derivative test. So the derivative test, the suitability of an iterative formula can be tested first by rearranging the formula such that it's in the form this, where fxn is a function of xn. The derivative f prime x of the function this is obtained. Now what I'm obtaining it to compare, if this derivative, when you substitute in the initial approximation, its magnitude is less than 1, it implies that the formula is suitable, because and to give convergent roots. But if the value is greater than 1, the formula will be unsuitable. So let's use that knowledge to see how this is done. So for question 2 says, given two iterative formulae, this and this, using x0 as 2, deduce a more suitable formula for solving the equation, and hence use the formula once to find the second approximation of the root correct to 3 decimal places. So the first formula was that we are going to first differentiate it to come up with this. Then I'll substitute my initial approximation to come up with 1.2, which is greater than 1. So what does that mean? For the second formula, which I'll conclude at the end, so for the second formula it is this. Therefore when I differentiate, I come up with this, and when I substitute the initial approximation, the value will be that. So this is less than 1. So what does that conclude? It means that this second formula is the one which is most suitable because its value is less than 1. So using that formula once, we shall come up with that, and that will be the root they wanted. So M1 for derivative, B1 for the substitution, M1 for derivative, B1 for, so M1 is for this derivative, B1 for substitution, B1 for conclusion, M1 for substitution, A1 for output to the required accuracy. So we have some of the books we recommend. So for Math 2, we recommend that book for paper 1 and this for paper 2. Then there also this question bank, which has questions which are arranged topical. So these books contain complete notes of depending on the syllabus. So for physics 1 we have that, physics 2 we have that, so the notes are also complete. For submath we have that. For O level we have this for S1 and S2, and this for S3 and S4. Then we also have question bank for O level physics and for A level physics, and for the math question bank. So those are the books we have so far written. So if you need any of those, contact the author on any of these lines. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on flowcharts. Therefore, if you are not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video on flowcharts has been uploaded. Otherwise, thank you for watching, and also if you know of any student who is not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.